are we online? Uh, are we online? Wait, I'm still having. I'm still trying to get used to that whole streaming thing. Come on. Uh, I should probably open the YouTube spot window so I get. Because I started sending the message before, so that way you don't have too much. Let's just say, uh, come on, too much empty noise at the beginning of the stream. Uh, and then I do that and I forget about actually checking if the stream's running. Come on, I'm not really. Uh, okay, let's check. Is someone there? Okay. Oh, okay. I found how to do it from OBS, and I see there's nobody. That's which is expected, of course. Uh, but I think it says it's. Can I check it? Uh, yeah, yeah. Okay, yeah. I am live. I can hear myself. Okay, cool. That's how you do that. And there's someone. Perfect. Perfect. I should be able to see the stream, to see the chat. Yeah, perfect. Well, hello everybody. So once again, coming in from a second casting dev stream, and this time it's let me actually type that properly. We are doing the compiler. So so I did end up not streaming yesterday. I was ill and couldn't really. I mean, wasn't really in a condition to stream. Um, that's why I might also sound a bit tired today. I didn't sleep super well, but I'm not ill anymore, so I can actually handle, the being live and probably not needing too many breaks. Um, but yeah, but I did make some progress on the compiler itself. That's what we, because that's what we do here. We make, we always making progress. Uh, so I will be showing that said progress to you. Oh, now, uh, let me check the timer. Castagne. Okay, perfect. That way, it's tracking the time, and I know how much tape time will be. So, last time, I still have the whiteboard. So, I did say, can, I did say that we did make the memory stacks. Everybody loves the memory stacks, that's right. We did them. We did some cast commands. We did state handles, which was nice, even though it took me some time to get down, that ref cell, all of that, because I ended up not really using it that much, Funny enough, maybe that's because I haven't done a lot of Rust development before. But yeah, but in any case, with the state handle, I was thinking, because I did a lot of thinking on the way and that, but I was saying I didn't like the fact that I had to borrow for simple access, but that state handle can actually help us in a later time to actually encapsulate those rules in a much more specific way. There's entities and the engine. Look, that's cool. We have the engine tick. We register our cast functions, and we started the Lex. And we so what I did yesterday uh, was this part, and I will be explaining it to you, and then working on this. So let's actually show that. So the idea here, let's remember our compiler. So if you remember last time I said there was 4 stages, I reduced it because I thought about it again. And I saw that we have there's one step that actually I don't really want to split, so it's gonna be fused. So remember, we have our CASP code. This is the file, and then we go through the lexer, which will give us a list of tokens. This is how we can, and with that, we don't need to spend a lot of time on the small stuff because we already have a lot of it done. Therefore, we then get to the next one, which is gonna be our intermediate representation, which we'll find a name for. So this one actually holds, instead of saying it like if I do this, it's gonna be if I say, for instance, add A and B, the lexer will turn that into a function called add, and an argument A, an argument B. That way, I don't need to focus on the small detail. I already have most of the syntax already done. So this is what the lexer does. And at the intermediate representation, I don't have that. I have I know that it's a function call that is of the function add, and my argument list is A and B, and with that I can also get directly some Cask code, which is all compiled Castagne code, some Cask commands that do map one-to-one. This is an important step, but we could use the Cask commands immediately, but then we have the last one, which is the optimizer or whatever, which gives us our final Cask code. So very nice, of course. The idea with all of this, of course, is that, well, we do need that intermediate representation because it will give us it's what will actually ensure our code is correct, and that's where we actually make sense of it, and that's where we have all of that. You can say I'm a bit tired. Yeah. The fun fact with me being tired is that I'm having trouble, thinking about regular stuff, but programming, that's okay. I can do that when I'm tired, which is why that's my job. That's why it's programming and not something like art or anything. I can do programming fairly well even if I'm tired, if I don't want to. But today I want to. Okay, but yeah, small aside on the side. Yeah, we have the function call. That way we can actually, know what's going on with this, and we can verify everything works properly, and from that we can generate our commands. Why do I want that to be all in here? Because if you're doing a compiler, it's probably like not the best idea. Like, first of all, the lexer here is a bit it's a bit advanced already. Like, you probably want something else. That's because we are a much more high context language, and because this intermediate representation here, it has an additional role, which is not something you usually find on other ones, and this is what actually gets fed to the editor. That way, the editor actually knows what's going on, It's not like, oh yeah, so get your code and get out. It's like, yeah, okay, you got an add function here. Let me put some drawings on the screen, especially if you have the hitbox function. Like if you remember Castagne itself, uh, like well actually let me just open Castagne. Wait, let me open Castagne itself. Oh, I forgot. But yeah, let me open Castagne itself quickly. So that way we have, you can show you what I'm talking about. So yeah, because Castagne is all, that's what we're gonna get. Like of course, with our characters and they doing they doing their attacks. But yeah, so the idea, if you remember, a Castagne script has let 5 feet. This attack, you can see this is my Castagne script. There's all of my functions here. I love them. That's how you work. Sorry, I can't make it bigger. But it's not really gonna be an issue here. We're not focusing on the code for that. But the idea is that I have some hitbox, and you can see I'm also drawing on the screen whenever there's an hitbox encountered. And because that's what Castagne actually makes that. That's part of what helps us, because that way, I can actually see, where's my hurt box on top of the character, where's the hitbox. Here, the effect, you can see there's a bit of a line here. That's where the effect's gonna be. That way I can adjust it in real time if I want to put it further away. Like if I replace it by a 5 and reload, you can see here, up, the effect moved, and I have this representation first. So that's the kind of stuff we want, because that accelerates development a whole lot. And on top of that, there's many other parts, but that's what we actually that's why you know what I'm talking about and why we actually need all of that, because that's how Castagne actually gets its efficiency. It's not only through the design, it's also through all of these tools. And that's why we want a strong compiler, so we can make a strong tools platform. And that's why it does need to know what's going on here with the functions. So therefore, that's why we will have the compiler be more complex. But this work is gonna pay off massively in the very near future. But yeah, because right now that's why the current compiler, or the current parser, more specifically, is having a lot of trouble. It's because it's doing a lot of this work. It's doing plus compiling, plus separating that in a way that's not really super advanced. It can happen, was cobbled together. It wasn't even meant to do that, to be quite honest. Like yeah, and it already splits there through states and stuff. But yeah, but at this moment, since we don't have an editor, we're still gonna be using like a regular text editor to make our Castagne 5s at the start, because we're gonna be remaking this editor. Because if I just get because my internet structure is not going to be able to read that immediately. So therefore, we will have some additional constraints that will come during a later refactor. Because, as I said, it's a bit hard to keep everything in mind, and especially at the start of the software. Let me justify my bad decisions, the fact that I didn't actually prepare everything. That's how. So if we remember, the thing is that the software here is it's very tricky to grow. It's a between architecture and botany, because you do need to make it grow. The thing is that at the start, when you don't have much of a base to build on, it's sometimes it's a bit weird. You kind of need to see also where the software kind of wants to go, because you can make an architecture, but the thing is that you can design, but is that the best solution? No, most likely not. Therefore, you do want to get that more what do you call it? You do want to get that little freedom, to let the best workflow emerge. Like if I did an architecture and then I see, oh, but I need to write 10 functions to do anything, that probably means I did something wrong with my architecture. And letting it grow a bit organically, but still, still guiding it, I think that's one of the better ways to do software. Although that's not something I really thought about too much here. That's just an intuition. But yeah, So anyway, we're gonna be sending that to the editor later, but that's also in a second time, because that means we also need to be a bit more robust on how we parse all of that. That way, the editor can actually check and see. But we're gonna get to it with time. And let's be honest, also, the files made by the editor are probably going to parse fairly well. So worst case scenario, you know, you can if you were editing stuff manually and that way it doesn't parse. Yeah, I mean you can also edit manually again, whatever. But yeah, so this is where I think that's called compiling actually. but yeah, we're gonna need a name for all of that. But yeah. Let's actually go back to that just later. I will show you what I did for the Lexer actually, because there was a few elements we had here, and then we'll start properly. So remember, cargo test. You can see we got a lot of tests. We got 56 because I added a lot of Lexer tests. Especially we got the branches. I didn't remember how I didn't figure out how to do that, but I ended up doing it in a nice way. So Lexer. So we got. So remember, I have my test here. I test line by line and find a token type. So we got the state name token. As you can see, I get column name of the state column, and I get a token type that say it's a state. This is the column. This is the thing. Perfect. Comment and documentation comments. And we got some specific words. Function name, which starts here, and with arguments. This is how I'm doing arguments, because we didn't have argument lists before. So let's check them out now. So you can see I've got one function call, and then I add two arguments. Like that way, whenever I stop getting arguments, that's when my function call ends. That's which makes it simpler for the parser. Then we got function call, and again more arguments. We got a full test that will actually do all of these lines. I've got a stop token at the end of each line. I don't know if I'm keeping that or not, but at the moment it's here. I think it's useful sometimes, probably. Maybe yes, maybe not. We'll see. That's why I don't want to overly go in. But yeah, branches are the trickier ones, because here, look, F5 column. That's a bit of a tricky way to parse it, because especially F5 is gonna be a word, and this is always a bit tricky to handle. So the way I'm doing that is actually, I'm translating it to a branch type, with here it's a frame branch, then an argument, and then I say branch start. That way I can actually, separate the start of the branch from the next tokens, because that could be a function call, that could be whatever. Yeah. So as you can see, I've got here F, it's got one branch, F, and with the commas, you got 3 arguments. If you have a range, 5 to 10, that's a single word, so that's also an argument. And I got negation. I don't know if I will be doing negation immediately, in the branches, because that's not part of of Castagne's code right now. But I think that's useful to have. Because I have plenty of places where I do a branch and then I do an else immediately. Might as well just get this out of the way. But yeah, it's passed. It's just not handled at the moment. I mean, nothing is handled at the moment, but you know what I'm saying. Yeah, we also got here with the modulo, which is going to be useful for F branches. Every branch can have. I mean, the parsing is done the same way, but the way we will interpret it in the semantic part is gonna be the very branch specific, because a modulo doesn't make sense for every branch. But yeah, so I did a lot of combinations. I also got the Viva branch, which is the F and V are gonna be the most important types of branches. You can kind of build a lot of the rest of the behavior with just that. So you got the because you got the here because with this allows us to test variables. So here 10 and 20, that's not variables, that's constants, but whatever. At this moment we don't really know yet. You can see I've got a comparison token type, which has a comparison operator. Here is a test that shouldn't work if you only have one equal. It says you got one equal, get better. I could allow the single equal to work. Do I want to? That's another question. But and yet you got the different than. Of course, here my font is using ligatures. That's an exclamation point and the equal. But yeah, that way we got different, superior, inferior, equal, inferior, equal. We got a V branch with a single parameter, which is kind of like C. So Rust doesn't allow that actually because they want to be more precise. But in Castagne, we already know the context and we can use C-type arguments, especially if you're using a Boolean. If you're using a Boolean, there's nothing to. I mean, even in Rust, you do that; it just works. You can't just put an integer, for instance. I've got also some other types of branches, flags. I've added the comma. I don't know if it's and or not. Whatever. We'll see. And or. Yeah, we'll get to it when we get to it. Base branches, input branches. I just check they are being passed. But yeah. Oh, so how does the Lexer do that? First of all, I got some additional Lexline tokens. So this is the Lexline token is the small part, is the more granular part, which does handle all the special characters and gets the words, the long word, which is a word that I haven't cut. And then we get to our token types with a state, command, document, argument, function call, branch, stop one. We got several branches, variable, frame, input, flag, and phase. Where how they are going to be used exactly, that's gonna come in at a later point. At the moment, we'll start with no branch. Yeah, comparison operator, you know what it is. I did implement a function on the branch type that does map the letter to the branch. We got the token. This is because here we only send token types. The token itself will have more information in it, which at the moment just the line number. That's just useful. But yeah, and we got our Lex script, which is what we send back, which has the list of tokens and errors. Because yeah, what something I added is errors. Now we have a Lexer error, which is an error from the compiler that just has a message and a line. There's nothing much more to it, but that means that instead of having of crashing, now we just report the error back, which is nice. But yeah, so that way we got this Lex code, which is the main function we use. You give it the code, a string of code, and it sends you back the Lex script. And it sends you answer the Lex script with its errors and messages. So that's what we do here. We just, as you can see, I just match the next line. If I got my token types, I just clone them and pass it to I just create one token for every token type I found. And then I go to, if it's, I push another stop token. If the line is not empty, if it's empty, I just ignore it. And if I got an error, I just add it to the error list. Lex line token, because that's, so that was That's where we get our Lex, small tokens. This is it's back the Lexing error. If we have escaping characters, we're still crashing. I need to go through. Uh, the error that can happen is for the special characters because I've because I put a list of characters that we might be using later. Uh, let's be honest, like right now, if you're doing programming, you're mostly using alphanumerics for words. At the moment, I'm not restraining it too much. If you're using weirdo symbols inside of your thing, like if you call your variable cash money with a dollar in the middle, you can asking for it. Don't use symbols too much. But that way you can use your emoji, your UTF-8 characters. You can write it in French, maybe in Japanese. I don't know. If I open up a file and it's written Kogeki in hiragana or kanji, like I'm not reading that code, but you can, or you can code in Greek. That would be something. Right. But yeah, so at this point, I just say, oh yeah, there's an error. Don't do that because we probably will be using some of these symbols, and I want that to be done early. You will notice we don't have the this one, the dash. Oh yeah, dash. That's what I was looking for yesterday. We don't have the dash because I like the dash. I like using it in words, but and it's used for some words like the ranges. So that means we also might not have the expressions. But do we really want expressions? That's another question. Remember that Castagne script is meant to be simple. If you put like a bajillion exceptions, that's not maybe not gonna be so fun anymore. But yeah. So, line tokens. So we have so it just adds the words. That's how it worked yesterday. It doesn't change. I've got some additional helper functions. We'll go through them just later. But yeah, we got in the Lex line. So of course, if you start with a comment, it just passes the comment. Here I crash, I panic because I don't, because that means the Lex line has done something bad here. Because if we got no comment, that's okay. But if we got a long word, that's okay. If we got something else, that means there's a bug and we want to catch it here. Same, we don't want to have more, but I guess that's, I can kind of remove that because that's caught later on. But yeah, first token, and depending if we're a doc comment or not, we do the correct one. Column. Column just does it says, oh yeah, that's a state name, and we're done with that. And if we have a word, that's where the stuff is going. So first of all, I got some. If you find the reserved keywords, if it's else, if it's endif, we do those. I reserved additional keywords. That way you. So is it gonna be the? That doesn't mean it's only gonna be some of these keywords. I just reserve them because they have a lot of meaning, and we don't want to let people use them before we are here. Yeah, let's put def here also. I forgot because we did use that one, and that means like if we do that, it prevents people from having their code stop working because we decide to use the keywords. So I'm just putting the ones that are most likely. If I decide to put character as a keyword later, for instance, that could break some code if it's not in the list here. But with everything in its time. But yeah, so that way yeah, we reserve them for later. Mostly really regular programming stuff. Let's put an if too. That way, while for loop do in case we want to do while. But yeah, no, why not? But yeah, probably not gonna do control flow in Castagne, but you know. Then we check if the last token is a column. That means we're doing a branch. If not, we're trying to do a function most likely. We're gonna check if it's good UX at a later time, but at the moment that means because if it's a branch and the branch logic is complicated, uh, we just delegate to next branch line. Same for the arguments. Like I'm checking, do I have a word and then a parenthesis? If I have that, I just add the function call and then I do the argument list. Then of course, if it doesn't find, if it's just one word or a word and something else, it will tell us the or line's invalid. Uh, yeah, and yeah, it checks that we at the end we did consume all of the tokens. That way we have we're sure we didn't miss anything. But yeah. So how does the is2 works? Well, first for the argument list, that's a bit easier. Basically, we just do is it if we got nothing, that means the function isn't closed properly. We send back an error like missing line. And if we the parenthesis closed, that means we are over. We're finished if the parenthesis closed. If we find a word, we get to we get the next token. I mean, we add the argument and then we get the next token. If it's a closed parenthesis, we continue because that way next loop we're finishing. If it's that way we get the next token and finishing the consume the next token and finish that. If it's a comma, we consume the comma and continue. If it's nothing of the two, that means something's weird's going on, and therefore we say there's an error. As you can see, we we're sending back errors all the time. As soon as we return an error, that's it. We stop parsing that line. That means the line either gives us a bunch of tokens or it gives us an error for the line. But that way we can actually get all the lines that have errors. And because Castagne script is pretty doesn't need like very strong grammar. Like if I have a problem on one line, it's not gonna affect the other ones. I mean, at this point, because if I forget the closing bracket, it might appear on a line a lot later. It might appear. It might tell me, yeah, I found function. That's not what I expected, but the problem is 5 lines earlier. In Castagne, that doesn't happen. So that's cool. For branch lines, that's a bit more complex. We're not going in detail, but basically, I'm starting because I know I'm starting with a word. That's what I have. I'm actually even sending the contents of the word. So the thing is that I start by getting the first branch letter and finding it and seeing if I know that branch. If I don't, I just send back an error. Once I have the branch, I just create a new word token with that, but without the. I mean, I recreate the word without that first character. And if there is still something, I do create my word token. If it's empty, I don't. That's why I don't have empty word tokens. And then I just push my branch type and iterate on the tokens. So I'm using the iterator a bit more manually here. But the idea is that then I match on the token. If it's a column, I'm done. I push the branch start and we return. If it's a word, we add an argument. If it's a comma, we check. If it's another word just after, we continue. But if it's something else, like for instance, you got comma, column, that's wrong. So we send back an error. And then here all of this is just the equals stuff. If I see an equals, I'm checking there's an equals after that. If I see an open chevron, I'm checking if I have an equal or not to see if it's just inferior or equal. Same for the closed. Exclamation. If I got an equals after, it's the difference operator. If not, it's just the negation. If I got percent, it's modulo. And if I got something else, I do an error. And if we get to the end here, that means there's no more tokens. That means the branch ended before we found it. Of course, I think this is unreachable code actually. Because there's because we did check for the column at the end, so therefore we'll always find a column. So therefore this is unreachable. Let me click on it. But yeah. That could be something, but we could maybe add that otherwise, like if we don't find an open parenthesis, maybe we will call this one and it will tell us, oh, your branch ended unexpectedly, instead of just handle it. Instead of just, oh, I don't recognize the line type, but that's not an issue too much. But yeah, and with that, that's what we were doing. So half an hour just to explain what I did last time. So, and from there, let's get to uh, let's get to the next part. Yeah, let's get to this next which is, yeah. Let's go back to this. By the way, if you have any questions, don't hesitate. I'm seeing the chat and just not seeing anybody talking it. Uh, but yeah, so that means we're gonna work on that intermediate representation. We're sending in the Lext script. We have the Lext script, and we get here in that intermediate representation. Let's find a cool name for that. I'm thinking semantic, because that's kind of what I'm doing. Of course, semantic, like we're always trying to make sense of stuff, so that might not be the best name, but semantic representation. I think that's a good name, because it does say we did make sense of it. Because at this point I don't know what I'm saying. Here I know exactly what I'm doing, so that's what we're gonna do. Because that means we can easily go from function call to commands, and we can reference from the commands. We can reference this, which will allow us to trace the execution later on down the line. At the moment, that's okay. By the way, our optimizer at this moment won't do anything. It would just take this and just send it back. Be like, yeah, I did the work. Just be done. Anyway, so here's us. So let's think a bit. More specifically, let me think, because I'm okay. Yeah, anything. So our semantic representation. We got a Lex script. And then we just iterate on every one of our tokens. And from there, what does the state representation want to know? The semantic representation wants to know. He wants to know the states. Of course, it can't really do anything without the states. Then what does it want? It wants our function calls. It wants some function calls for each one of those states. So, I mean, that's kind of what happens here. First of all, we do need to get one state first to start. So, in fact, Castagne code's a bit, because we got our character. This should be the first. This should actually be the first one you get, like period. That should be if you don't start with the character, because this is the header, which means we might need to parse it differently, but we kinda forget about that. We also got your variables blocks. This is gonna be more a bit special for this new edition, we're also gonna ignore. We actually we won't be able to ignore it for too long. But let's. Actually, we won't be able to ignore it at all. But yeah, but we will create some fake variables to start out with. That's how we're gonna be doing stuff. Yeah. Fake variables. That way I can actually, start parsing before starting to add all of these. Then, because yeah, that means we also need our symbol tables. Because yeah, well, we are gonna be checking stuff one by one. Because yeah, because at this point, like yeah, because before we can't compile and actually, get the cast commands, we're gonna need that symbol table because that's where our variables go, that's where our state name goes, and we can't really figure out if something's correct before we parse that whole file again and created. That means we need to uh, find the states. Get the state actions, let's call them like that, the actions and functions at the branches. Well, of course, not doing branches first. Or first order of business gonna be just one state, and it does add. It adds A and B, and it puts it into C. Well, yeah. But yeah, we got 4 variables. We're using them. He gets the state action. Gets variables. This is step 1. Step 2. Step 2. He does the checks. That's where you actually get we like do the variables exist that's important. Yeah, well, that's kind of what it does. It probably does something else. Like here we're getting syntax errors because with the Lexer got us grammar errors, like basic. I think here is like, oh, you said something, but it doesn't make sense or whatever. Might be actually opposite. Like here you didn't write it correctly. You don't the Lexer catches stuff when you don't write it correctly. This first step catches stuff when you when you did an error in what you wanted to say, like where it doesn't make sense what you're telling the compiler to do. And here we're catching the mistakes. Like here it's you don't know how to talk. Here it's you're not making sense. Here it's you're wrong. And if you go all of that, then on step 3, we're getting an actual representation that works. Of course, because we got this editor thing, that means that we kinda need all of these 3 to do result in the editor. Kind of figuring out. Actually, same thing. Even if we get that, we do need the editor to be able to display it. That's why we are. But that's for a next step. As for another step that we won't be making right now today, we will be figuring it out later. Maybe we don't want that. maybe we will progress with errors. Of course, if there is errors, the cast commands only get produced when there's no errors at all. Like when, okay, that's what we want to do. We know what we want to do. That's good. But yeah, that means there might be some reworking going on. That's why we also don't really want to optimize anything at the moment until we got the editor, because one of the main optimizations that's gonna happen, like it's actually inlining, because we know one of the big parts of Castagne is calling out the state scripts as helpers, and this is a static inlining of those commands. Because I mean we can do that. So let's. I mean it's not like memory is like it's not gonna take memory, like it's not that space in memory like we. Okay, maybe you took your function that's 10 commands. Okay, 50. Wow, we got 50 bytes, maybe a bit more, but we're not. Uh, your code's not gonna take that much space. We can assume the user has probably at least 1 giga of memory when he's running a video game. Uh, so because it's gonna, I mean, any model's gonna be bigger than our code. We're not at doing electronics with all that. So if it is too big, we will see. But I think performance here is what matters, and we don't want to do dispatch and going back and forth in memory. We want to go fast. But yeah, so it's only static dispatch, and that's very important for Castagne code because it's not gonna be able to handle it by itself, and therefore that's a big optimization part, and I don't want to do that too early because then I have problems. Because if I do more analysis, because before I have the editor and be able to know that where how my structure works, that might actually require me to do a lot more refactoring. So at the moment we at step one. We're gonna do step one. And yeah, of course, what am I even saying? Of course, we're gonna do step one, and we're gonna then progress through the steps one by one, and that way we can compile our little code here, and then we'll add the special cases for the variables. We'll add the character block, especially because that's where Castagne gets actually really fun. Because this has a very important instruction here, which is a skeleton. What's the skeleton? That's another file. Super bright. Yeah, we're gonna have a lot of fun with that. Which means also, as a later optimization, we probably want to be able to output partial results. That way we don't need to parse the skeleton again. We already know it's symbol table. We can get through it, but that's not what we do today. That's already tiring me out, and we'll see how long this stream is. Probably not as long as the previous one, because probably won't be focused as long. So now let's at least progress this and create our semantic states, semantic representation. Yeah, because this part we skip because we don't have variables yet, but states. We do find our states. We do find our state actions. From that, we will use a quick check here. Because we do variables have oh yeah, forgot the correct types. We don't care right now. But yeah, let's get to it. So let's call it semantic. That way we got the semantic representation. let's use. One thing I want to do first is actually move that Lexer error. I want to make it a compiler error. That's not really an issue. We're gonna be moving it earlier. That way, all errors have the same representation, which is gonna be. No, let's not forget it's public. And instead of new, it's called Lexer, which will return a compiler error. That way, we can add some types later. Let's do it that way. So that way we can actually we're gonna assume that words we can make it change as we need to. Of course. So we're gonna replace every Lexer with compiler error. Oops. And every compiler error with Lexer error. That should work. Wait, first the tests. The tests don't have that. Oh, maybe they do. Lexer, yeah, error message. I don't think they have an issue. Let's do cargo test to see if it's still compiling. We're not compiling. What's going on? Use. What the? Is the Alexa not using anything from above it? Yeah, that will do it. Perfect. Perfect. Then let's continue. We don't need those Rexer tests anymore. Maybe we do actually. That's fine. Sometimes removing everything we don't need. Okay. So semantic representation. Let's first start with the step one. How do we call it? Whatever. It's not public structure, of course. Let's not forget about so that your brain's already starting to get out. Oh, today's objective is getting a good night of sleep. But yeah, step one, we're getting. Step one is getting that state. So we're getting a Lex script as an input and iterating on all that. Okay, perfect. I will give it a better name later. Just trying to get through today. I don't even know what we're planning yet. But yeah, for iterate, probably. Uh, So we're trying to get with our current state. So let's force that first to be a character. But no. We're taking a peekable iterator. Because 4 will take ownership of that token's variable, and we do want to access it to be able to pick if it's a correct one, probably, most likely, whatever. Because the thing is, when you're tired, it's hard to start stuff. You know, when you start it, it's a lot easier to catch. What am I even saying? Whatever. But we're gonna assume the state is uh, we're gonna assume the state's correct. First state name. State name is gonna have the tokens. It's actually gonna be a oh, interesting. Yeah, actually, yeah. Okay, could be. So that's where we'll check for the character first. Therefore, at this point, we know our state. We know which state we're part of. So we don't need to have it be an option. We always have a state here. We name and semantic state. Cool. I'm staying state name. Because the semantic state is the one that's gonna get, all of these tokens. Basically, we're building our states. Our variables blocks and I say, is the variable block, is the character block different types of states? Maybe yes, maybe not. Maybe it's a state with a specific thing. Maybe we'll have blocks, because branches might have two blocks. We will get back to that when we get back to that. Because that way, we probably, yeah. Let's actually, we're actually gonna be having a bit of a structure here. Let's go back to the table. Wait. Okay, so let's get. Yeah, sorry, I had a message. Yeah, yeah, it's a tree because every one of our states, gonna be like there's gonna be like a sort of graph structure, like I mean, but yeah, because we're getting the function calls, we anything is a list, function, branch. There's plenty of branches, but each branch, once you got a branch, you can divert. And I think it's good to have as a primitive because we're gonna need that quite a lot. It's gonna be the call order state. The condition. There's several branches with code, and there's also that's call order state. That's kind of how it goes. How will we handle that? Do we keep that or do we know that for now? Well, in any case, that's a second thing. Yeah, that means our primitives are gonna be function call, branch, call order state. That's not that many because we can also declare variables. I mean, but this one is not part of the script block, and this is a script block too. So we got semantics block or script block. Oh, let's call it semantics block because we're in the semantics. So that means a state has one semantic block, and when we need that means that if you call another state, we're getting that state's semantic block, and a branch has a few semantic blocks here too. And when we want to pass this to a cool Cas script, that we're gonna go through the semantic blocks. And in fact, if we go back to the steps, so step one is going from the next script to our semantic state semantic state. Step two is we take the semantic states and we just check them. We don't change them. We just check that it works. We check there's no loop. We check there's nothing of the sort. Because until then we don't really know. We might get several checking steps. But this is the checking state. And step three, but that means we already have a semantic representation here, and we just continue with that. And in step three, that's where we get the cask commands that are passed. That's why. So that means we still have a semantic representation, and then it's in optimizer we just go from the semantic representation to an optimized cask script, which might that's actually very nice, because all of this here is the semantic representation, and that means that we can always send it to the editor. So that means if we can pass a Lex script that has errors into a semantic representation, the editor works, which is something I was a bit worried about, but it kind of falls into place because the idea is that I did the design, I know I want to have that, but sometimes the detail don't appear too easily. You can do that on paper. It's not like I wrote any code, but it kind of helps get the brain going, and I got enough experience that it doesn't end up too bad when that happens. I mean, it's not about. Yeah. Just something real quick. That's called interruptions. It's important. Just need to check something real quick on phone. But yeah, so Lex script, semantic state, semantic block. Let's see here. That also means we can make our compiler errors. Well, let's change between semantic error and something else later. But yeah, okay, so we got our tokens, and we know we have a state. So we have the semantic state, and we element. So the block is composed of semantic elements, Each one of these is gonna be doing, but we got the function call. That's our main one. Got the branch, and we got the state call or whatever. If we're gonna add elements to it, but a semantic block is gonna be basically just it's gonna be a list of elements. Do we actually need that? Actually, basically a vector of semantic element, I believe. Do we want to keep that separate? Can we implement stuff on that? Actually, that's an excellent question. Can I do? I can. Superb. I don't think I need too much on top of that. Because it's basically just a list of elements, and I might want to have some additional functions, but I don't have data added specifically to the element. Do comments, good question, do comments get a part of, let's ignore comments for now. I mean that might sound stupid they said like that, but if the editor has to access it, he kind of want to have the comments, especially the doc comments, because that's what the editor will actually look for. Yeah. Add element. Because of course we have our function call, but maybe it will have function name and argument list. So it's gonna everything's gonna have more of these. But we will handle all of these as they come. Because we got two branch types actually, because we got the if else regular branch, and we got the the multiple branch, whatever, or the sequential stuff. But yeah. Yeah, so parsing compile elements, that's a better name. But yeah. Semantic states as block, it's a semantic block. Block dot push. Let's just match on that token. It should compile. Oh yeah, of course it compiles. We haven't been doing. It doesn't know it exists. Of course it does. God. There we go. Now we got errors. euros. Oh yeah, but the string from, but let's, because we're kind here, let's just get the string like so. I don't think it's here because otherwise we can't reformat stuff. The semantic state missing. No, it's like string from this there. Oh yeah, right. Yeah, okay, so we can't really do that. That's actually, I think that's the new type pattern, or whatever they wanna call it. Yeah. So basically what we can do here is has it as a double. That way we can provide elements. Okay, so structures are not public. We got one. I forgot to do that. To make these public. Token type public. I think most of them are going to be public actually. Like there's no reason to hide them, although there's that's internal implementation detail. Not exactly sure. I'm not really good enough at first to know about details like that. Everything's public. Not the fields, but function here. You can access the classes. So okay. Maybe new type patterns better. Maybe I should actually look it up, but so just because we're here in private, that means we can get we can figure stuff like this as we go on. Let's just do an add element. Let's run that. Yeah, okay, cool. This should be okay. Much. Okay, so this is a private field and it's not buying elements. Okay. Yeah, that's oh yeah, private field, yeah. Everything. Should it be public? Should the list of tokens be public? This one, just data structure. These two are public. That way we know if we have errors or not. We ignore the errors for now. It's a private field. The thing is here we're doing like very light structures. We don't really need to have them hidden. Like that's it's lines and stuff. Okay, so yeah, okay, perfect. It does we're not covering all of these. And therefore okay, so first of all we're gonna do a declare state with the that way we don't need to have all of these. That way because we're gonna need to declare states fairly often. So let's just build the boundary right now and just create that. And this is actually a result, which could be a semantic state or compiler error. Of course, at the moment it's not, but you know, if two states have the same name, you want to raise an error. And yeah, pretty much. You want to raise an error. So do you want to stop at each error? That's another question that we might or might not want. Because actually, yeah, we don't want to have an error at the end. We don't want to have an error at the end. We want a semantic representation, which might have errors in it, but it's, because yeah, here that means all of these don't work. We, yeah, because we want to figure out, you know, as we go on, we put the errors back, but we yeah. Actually, yeah, that same case, that's not an operation that fails. Yeah, I'm starting to understand the implementation. So I need to start to understand the implementation we want. Because yeah, the semantic representation here, it's gonna have errors. But if you declare a state here, uh, like if the state exists, you want to get you want to still make that state, because otherwise the editor won't be able to see it, and we don't want to stop at the first error. We want to catch all the errors we can. Uh, therefore, oh, yeah, yeah, we're passing a semantic block. I think that's why the stop tokens are useful, because you do want to pass that block. We want to pass the block, and for that we do need our iterator, or the pickable iterator. So we want to check the next token if it's okay. But at the moment we only have one block. Do we need to? But in any case, we take ownership of self. Same thing here. We have ownership of self. If it exists, we do an error and we create a new state name that has a different name. But in the semantic representation, let's put it down here with the. We got our arrows, which are compiler arrow, which is a vector. Compiler arrows. We got our states, which is a vector of semantic state. There we go. And the if we have got the hash state, maybe not a vector, maybe it's a hash map. We got it, but we got our hash state, which returns a boolean. And so if it has a state, we will, if it has the, if I take a short of it by just after this line, if it has the state name, we return declare state with format. Yeah, with a suffix. That means that if we have 50 times the same thing, you're gonna have the state A, we're gonna have A, same name, same name, same name. Just go it like this. The more the more underscores you have, the more stupid your state is, but that way it does know, it says, oh yeah, that's that. If you got one that's also called like that and happens later, well, I mean, at some point, just, I mean, we're already in a degraded state. If you're if you're doing this to yourself, yeah, well, you cannot deserve it. Uh, you know, remember the user is also responsible at this point. Here for now, we will just crash if we take this one. Otherwise, we want to add it to the list. Okay. Small toilet break. Be right back. Oh yeah, I got the. I made it a bit better than the big. A bit better than the stream cut. It does cut my microphone, but because the stream cut does look like I'm not here for a while. This is for all the short breaks. This is just that. Usually we get. I see people usually leave around that time. That's because that way it might sound like a bigger deal than it is. But yeah, be right back in a couple of minutes. Hey, we're back. We're back at it. So, let's see. Thought about it. What's yeah, hash map. Yeah, that's where I was. Oh, anyway. So, hash map. Let's use that. Not having very good posture today. So just thinking. I think that chair could be a bit further in front. Yeah, that's where I am. Because I tend to stand a bit too upright. Sometimes I slouch a bit forward. Depends on how the chairs. Use ST into collections. Hash map. I think it needs to be owned. I haven't used, actually, now that I think of it, I haven't used the hash map in the Rust that much. Anyway, we're gonna. Does it need to return a semantic representation? Step one. Just gonna do semantic representation here. Because that's where we got the new. Because we don't send errors back anymore, we're gonna have a actually gonna make it a bit easier on ourselves. Let's just take a string and do all the rest here. Because if we have an empty script, like it's not like we can do much with it. So in this case, we can return. We get another if. So here we check the first. We want that first thing to be character, and then we can have all the tokens. We can have empty states and stuff, but we want the first one to be the character. If nothing's said, hey, actually, that's an excellent question. Do I want it to be a character block, or do I want all my casting script to start with character, or is that one of the state? Dang it, that's a good question. But I do want everything. Yeah, I do want that because that way I can edit it better. And if I have no state token after that, it's still, I'm sure I get my character state. That's how we get in through. The first state name is always going to be character. I'm always gonna have at least one character. So yeah, actually, yeah, that's just an additional check for eating that first token. Okay, I'm starting to get in the rhythm. way the error is a bit more understandable, because basically that's what we do. It's still the same idea. Here I can use the first state name. And there we go. So this is my state name. So in that we do declare state. You see, that's how we do that. Get a string, I guess. Wait, it's interesting in both cases, so let's do. We're gonna be giving that ownership when we do that, therefore let's do it here. That way we're actually definitely sure our state exists. And when we do a declare state, we don't get a semantic state, we get a reference to the semantic state, a mutable reference to the semantic state actually. Yeah. I think that's what it is. Oh, so we'll get an issue fairly quickly here. Maybe. Will Rust be annoying, or will Rust do it nicely? That's the second question. If we get an RC, I'm gonna have issue. Okay, so we added to. Okay, so anyway, because okay, so if it exists, we have an error, but we'll say we don't. Say we don't, and we can have to. At the moment, we're using string identifiers because that's kind of what the symbol table here will have to be doing. And which one it refers, because we're gonna have like maybe state specific stuff, but everything in its own time. At the moment, we're gonna say it's global, and then we're gonna merge the files. Actually, let's see how bad we are right now with the. Okay, so we're not doing that, but yeah, let's put it as a to do. That way it stays in here. Semantic state new. Yeah, of course we don't because we didn't add it to the list, and that's where we used a really good browser and get the hash map. Contains key. Okay. Wait, there's the entry API. Yeah, I forgot about that. This will insert its contains key, which it's just gonna be useful anyway. So let's keep it here. But declare state, actually, we can do that in one line, which is gonna be funnier. Which is gonna be the entry API instead of getting setting up the here moving keys and the values. Entry or insert. So player stats dot entry or insert. Self states entry state. I guess this one can be like in on STR because they got this. That's a bit weird, I guess, but yeah, let's keep it up. Because yeah, the STR maybe that's better. And we're getting or insert. Wait. No, it's not an or insert. Actually, no, I'm kind of doing it. I'm doing it the correct way here already. Because we do want to add it to the hash map and then get it back, but with a different name. Because that's where if it doesn't work, we want a recursive call. Right. I don't know if I see that someone has joined the Discord, but still doesn't have a role. But it just joined here. Let me see. If it doesn't have a role anyway, the bot containment system should be working, and we'll see if it does. Hopefully that will be tested. I'll leave it for now. We'll see. Maybe it will wake up in 2 weeks. Get declare state. Add it to the list. If it's here, it's self point insert semantic state. But how can we? Can I just I can just access it like so. You can see the difference with the other day, because the other day I was well, not in the not at the best form either, but I was a bit more focused. Here you can see I'm having a bit trouble of explaining what I'm thinking at the same time. So that might be here, but we can actually slice through it here. So let's do server state name, and we're not actually, and we forgot the state. It's not the self insert is self states insert. Expected str font string. Okay, font semantic state. Oh yeah, but I can borrow it as. Does that work? Will I get issues? Argument one of type string is missing. Oh yeah, don't be an idiot. I mean, we're using strings anyway, because we're grabbing this from the other one. Yeah, string. Okay, six. First token data moves here. Okay. First token dot t type. We're getting lots of warnings here. It's a bit tricky to find what we're actually doing here. So mod, engine mod, client 3. We're not using that. Goodbye. We are not using that, most likely. Uh, good, goodbye to. Let's get here. That's warnings, always nice. Okay, and if statement, we need to dereference that. A bit time. 61. I guess we're cloning that one, otherwise we don't have access to it. Cannot borrow as mutable. Why not? Get mute. Yeah, that's oh perfect. Yeah, okay. I get this as mutable. Consider cloning the value. Yeah, okay, yeah, it's moved here. Yeah, so I did figure out that we will need to clone it, otherwise it won't work. Can I do it that way? Or, or do I need to clone it twice? Oh, because I'm using it just after, yeah. Right. Cloning it twice. For warnings, let's remove that. It's in commands. Doesn't use RC and red cell. Lexer doesn't use display or RC. Memory doesn't use anything from above it? Dang. Maybe it will someday, but not using RC nor ref cell here. And we're not using RC and the Lexer. This removes some warnings. But the rest here is it's this one's gonna be for when we put the string type in it. Probably actually that's probably a good point at some to actually do it early. Okay, so we have to derive debug for token, or we can just get the token type directly. So 89. Does this work? Last one. Gets mutable and ah, yay! So now we got a bunch of warnings, but we can't really care too much here because this for the binary. Oh, that's the binary crate actually putting in that warning saying, oh yeah, I'm not using any of that. Can I actually? Good question. Can I just because if I do that, that means if I'm cargo building, it generated 50 warnings. I'll just skip back to the main. Okay. Okay. So we got that. I'll put test here. Okay, wait. Test still pass. Of course, I didn't do any other tests. You're gonna have them at the end. But that means that we managed to get the semantic state here. Here's the moment of truth. No, that's here because if we match on another state, that's because this is what we actually need to do. It's state equals clear state name. So because otherwise it's gonna tell, oh yeah, we're moving these. I'm gonna ask about it quite often now that I think of it, but yeah. And here, this is not gonna compile. Yeah, because it will move the value. It's behind. Can move. Okay, perfect. Yeah. This is why we will actually do. We cut into in str, and we put it not as clone but to string. To string, don't need the value. We can keep it without a string here. We can declare it ISO. Two errors now. Expected string. Okay, cool. Cool. That means it works. That means we do get some new states each time we do get through one. We're gonna do because like I can do a test, but like the only test I can think of that's not super annoying to set up is like an end-to-end test of the semantics presentation. Like get the Castagne compiler at the end. Uh, like check, do we get the correct cast commands when we get here? But yeah. Anyway, so if we get a new state, we continue. Otherwise, I think we just I think we kind of pass the block. I'm not sure. Yeah, give it the tokens here. Reference to auto the token iterator. At the moment, let's. I mean, we will refactor this. Oh, we can just do it now. That's also works because we are. This token is a whole. How did I do that then? Because it was a bit complicated. As a parameter, yeah. It was that's what it was. Let's put a little like let's put it as a type, and it's easier to understand what's going on. For any other token, yeah, actually no, think of it, it's not. Yeah, no, parse block. If we get the next Next token has a state here. That means all errors stop in their state, which is very nice for us. So that it will return as soon as if it peaks at the next token's state, it will say that it won't. It actually won't, yeah. Yeah, and also, oh yeah. Yeah, so I don't want to make a match here, a match instruction. I want to peek at the next one at the start of the pass block. If I want a token or I get none, I'm returning. And returning a semantic block. Else, I continue. And then I can loop through all of that. That's my loop. I loop until there's no tokens left. So this is my exit condition, my while. Actually, while, no, that's just a while instruction, I'm stupid. While it's not either a state or like that's a bit trickier to write down. Because that's not just a match. It's if it's none or if token types a state, yeah. Yeah, so I can't really do that here. Yeah, so what I'm looping, and if uh, then then let's type here and then here if it and here's my matches. So I check if the token type wait, don't care which one. Here I also return. we kind of need to do some additional checks for branches because, like, if you have an else that's still open, that's gonna be an issue, but this is not something we do care right now. Here we'll match on T, which is gonna be which gonna match on sorry, the took on, and because we know that it's not none, we know there's one, so we can do let token equals what token stop next, and which allows us to match directly on its type, and this is where we put our to do. It's not handling anything else, which is why here, now that we got our state, and then we can we're gonna we loop still on that tokens here, but also image equals tokens. It's every one of these obviously has a thing. Okay, so yeah. So first token we declare our state, and then we pass that block. Pass that script because that's our public function, the one that does everything else. We do want to pass that block. We don't need we don't need the state here. We just need the tokens iterator, and just yeah, I can access the private thing. So it's state dot actually, yeah, no, I don't want to. I do still want that mutation because that way I know which one I'm passing, and therefore I can state the errors as they happen. Hmm. Yeah. Okay, that should be this one's an error for the programmer. That means the compiler screwed up. Oh, that's super smart. Wow. It's able to infer it from the indentation. That's because I forgot to close one here. Wow. Very impressed actually. Yeah. But we don't get semantic block here. We just we'll make it. We'll push it through, through, through. Oh wait, we do want to send a semantic block, but we want the state to be able to get our errors to the state. That's because errors can be a bit stateful because we kind of need that. Oh, of this. So if the block's empty, the block's empty. Yeah. Okay. First of all, I forgot to unwrap the token. It's here. Reaching a mutable ball. So do keep state. Why does it? Oh, ending. Borrowing self to get that mutable. Actually, let's be. No, oh, that's not really good because I was said I could make a slice, of the tokens, and then actually no, actually yeah, that's actually a bit smarter. Because he I'm trying to. It doesn't like the fact that I'm using the bow several times, which is a bit of specific stuff, which is a bit special. But what I'm thinking, and what I'm thinking here is that we actually don't need that. We can actually we should make it in several steps, right? So instead of having one state and keeping that together, we're actually gonna get several iterators, one for each state. That way, that compiler will be able to be run in parallel in the future. What do I mean? Well, that's it's gonna also solve the small problem here. But yeah, check this out. This is this because this is actually a bit smart. Like kind of forces me to get some good patterns. But the idea is that we have our state code. That's we got state one, which got add to add whatever, and we got state two, which does sub whatever. The thing is that here right now I'm kind of parsing everything here. I'm finding a state name, and then I say okay, parse the block, and I do that block parsing until I arrive at the end of that iterator, yeah, which I find a new state name, and then I go back to here and I continue and do that again, parse the block. What's actually something that we could do here that can also solve this a bit is that if instead of doing that we would simply big simply if we start with all of these tokens and just split them here, like split them at each state. You get it? That way, all of these, this is independent, this is independent, and that means they can be treated separately, which is actually going to make it much simpler for us to parse our script, because I don't need to. First of all, if I find another state token, I can just crash out because that shouldn't happen. So this makes the structure a bit. It doesn't actually make our structure heavier, but that means that every one of these is independent. That means my state block. I don't need to declare my state immediately. I can just create my state separately, and at the end, once I've got all these funny list of states, I can just then merge that together and create my semantic representation, which is of course it is very nice. We like that. This also means that all of these can run in parallel, which will be able to improve our compilation time later, because we want to have a very short compilation time. That's going to be one of the major parts of the designs, that we want to be able to iterate super quickly. Right now it compiles in like 1, 2, 3 seconds, which is all right, but it's a bit slow. And that's with some, I mean, it does optimizations, but it also tries to not overcompile, so, but yeah. So that means each one of these, instead of having this big semantic representation and adding all errors into it, will be instead parsing these all, gonna have a parse state function. And yeah, that's what we'll be doing today then. That's really cool actually. Yeah. We haven't even done the first step. Okay, let's because well, in this case, here we don't even need to declare the state. We can just check that. Yeah, indeed. Yeah, actually, even it's a we peek at the first token. So now we open the Rust documentation page and we search for iterator. That's not so. I was not looking for the module. I was looking for iterator. Do we have a split function? I hope we do. That sounds like something you want to have, because slices do have that. Because it's partitioned. Here's predicate. Because you can collect, of course, the elements and just create. I don't really like it, but let's just. Uh, yeah, I don't like it, but we'll just clone the tokens. It's not the best way because it's read-only, and like we could just read them together one by one, but it's you're gonna get some better use out of this if we just do it that way. Do why let's token doc next. That's why the declare state here is gonna be a bit different because we're gonna send it the state itself instead of getting a reference to the mid semantic state because that's that way because here actually the semantic state was always giving a reference. That way it wasn't really independent. You gave that. You could make it independent depending on what you. But here that means that this function here that passes, it doesn't know about uh, any of those other blocks of the pass state, pass block. But actually it doesn't know about that because that way you can do pass block, etc. So it's all of these don't know about each other because the only one that knows is gonna be the the first step, which is gonna start all of these separately, and then at the end we put the work together, which means that any one of these can't affect the other. Uh, we don't really need it to be parallel, let's be honest, but it's not a bad way. If we just had the iterator being able to be a bit more, you know, separate, I guess we can though technically, but can we just send that? Yeah, actually. Actually, instead of copying the tokens and working together like this, we can. Well, there's gonna be a whole lot of tokens to copy. What happens when you clone an iterator? Just question, can you clone an iterator? Yeah, you do, yeah, definitely. You can clone. Oh, inspect, what does that method do? Okay, that's what it does. Oh, right. What's the peekable be cloned? Yeah, it can be cloned. So we are peeking at the next token where we can. So we don't do next immediately. We just match. If it's a state, what we do here is that we do if we're at the end, we don't need to add that. But at the beginning, we don't have anything, but we start here and we push and we tokens and we clone. We clone it. We clone it, and then we continue. Let's do this deflet because it's we're just cloning this in this case, and then we do tokens next. So that way we get enable state iterators and then form it for state iterators, and then we do self.parseState, and we send in the state iterator, the state iterator. By passing the state. We don't need to borrow self-mutably for that, I think. But we are sending back a semantic state. Semantic state probably has its own errors because that way we can associate the state with its errors. That way, you know, it's gonna be easier to know what block has what error. And here we get our four tokens, which is gonna be our peekable token iterator. Which means at this point, at the end, we just have one for each. So that means that we got one for because when we arrive here, we just peeked at it, so we don't know it. We just check that it is a character token first. If there is an error, do you get that? We do that same. So this is the character state, and because we're gonna do a lot of that same stuff here. We don't check for the exact state name, but that way, because that way we do have this error in general that does that gets added to the errors of the semantic representation, but we also get the state errors themselves just later. Okay. But yeah, and so, but this here we do check if we have a character, because here we don't stop the parsing because we do need that robust evaluation. Say, we do need that robust evaluation. Okay, some lines we don't know what's going on, so we don't even parse them, but here we kind of need to. Actually, probably want to do a token type for unparsed lines. That way we will be able to edit stuff when we do make mistakes, but we'll keep it down here. Alright, you know, let's that way it's always inside it. Yeah, that's because yeah, no, that we while we have an unparsable element, of course we won't do that, but that does mean we even still keep the comments there? Yeah, we do because we do keep the comments because we will need them for the editor. So it does want to know. Like, okay, we kind of don't care about them most of the time, you know, especially if something is impossible, it's just impossible, you know, there's nothing more to it than that. But if it's impossible, you do want to keep it around so we can edit it. This is gonna be yeah, if the because they're in the Rolex code, if it's empty, but if it's an error, if it's an error, that means one on one end all line isn't empty. If it's empty, we can I mean the next line would catch it. But if it's not empty, we want to add the we want to push a token here. Unpassable line and line ID. And we're also putting it we put stop token because we love stop tokens, which means that we still get a representation of that line that goes through with us, and we will be getting it here as an unpassable, which will allow us after that to just display it in some way in the editor. Yeah. Small aside. I shouldn't do too much any of either sides because after that I'll get just lost. We don't need we don't need a state for that. We just need a tokens iterator, of course. The problem with the tokens iterator here is that it doesn't stop at that part. I guess we could. I guess we could actually. Yeah. Actually could, yeah, by doing some but it's gonna be slower anyway. Like yeah, we don't want to stop the iterator because we're gonna need to collect and stuff like that. You know, we just will take care of if we find a new state. But that means we're kind of starting to have that happen a lot. Uh, if it's the end of a state, if it's end of a block, that way we get that. It's easier, and we get it's an option token. I believe that's a type. Once we love that, we just return if it matches. Then here we if it matches at the end of the block, that can be stuff like ND, else. We do it that when it comes to that, at the moment we just gonna just send it back the end of state. This is not nice helper function, so we can change it with let's call it next instead of peak because it's we got the pass block and we got the pass state. Now it's probably gonna be a function we'll have to change a bit. With add state first of all. We don't return anything. State has its own name inside of it. Well, one by one. Just pass it because we're gonna add it too. Here I'm just trying to report the first name that's not here. So because here I put it at none because if we don't have, because that's why it's null. But if I come here inside it to, to destroy the collision and I see I is the first loop, I just get the name here and then I do if some name, then I can do my self error and format it. That way we get all error. That's good, and this will, and that way I can continue with my semantic state. So let's stay. You're gonna need that one a lot. First of all, let's do if first of all, if this happens, if we don't have anything, we panic because that means we're sending. Oh wait, no. No, because we don't, because we're gonna get if we get to the, we are at the start of the state, therefore do get. But if we do the else there, we're gonna have an issue, a major issue even. Uh, because if we add that, it's gonna go decode passing here for reason. That way the state still gets fed properly, I guess. A bit more robust. Of course, if we have at least one error, we won't get the compiled stuff because we don't check for errors before. Yeah. Okay, state name, tokens. Uh, this case, we're good, and we consume that token. That's what we do, because here we check if the first token is a state name, we do consume it right now, but if we don't, we do an error. And we say here, and those more sound like it does sound more like a programming error actually, because we did cut on these states. Yeah, that definitely is a programming error if it happens. It is a programming error. We don't want that. We want to crash. We want to crash and burn. I'm being too nice. We don't want to state error. We want to panic. Oh, we don't even need that. We just do next immediately. And then we also bring the errors back. It's not a reason because we both get the errors we put along the way. Can I just put it like, yeah, okay. Yeah, because we're passing a state, so we already have used the errors on the way. So I can probably decompose it like this. Let's check. Let's check our, let's say 6 errors, 19, okay, yeah. Okay, well, first of all, declare state, pass state, yeah. Right. Yeah, first of all, all of these blocks can yeah, I speak good, speak very well, to do add state to the list and errors to, okay, yeah, that's good enough. Let's go that way. We have 17 errors. Expected here, we got options. Just forgot my gamma. Need to put a mutable. Yeah, so I'm gonna open it on the second screen because there's there's quite a lot of errors and a lot of them are really small, so let's not just let's see. Okay, so first of all we got a small mismatch type on line 1, 2, because we forgot to send in the reference. Okay, let's start at the beginning of the start. Okay, so this it. First of all, here in the semantic state, I need to add the error function, which adds okay. Yeah. Oh yeah. I added a bunch of lines, so it's here. Actually, it doesn't know. It's not really new with semantics. Just yeah, like so. That's 11 errors now because there's already a couple here. Because it couldn't tell the type here, so a lot of them will be if len none equals error. Ah, yeah. Name control let. And then I got an error on the lexer with the unparsable. It's line.close. This thing's on. This thing because we got an str. So it's yeah, but only 7 errors remaining. Mismatch types only. 3. Expect str font string. Right, actually, instead of as a str, what happens if I borrow it? I think it coerces it into the correct one. Yeah, it does. Expected option string found string. If let. Yeah. There's gonna be a couple ones. Well, one. Okay, so while this is a bit weird in construction, it's because we're gonna add stuff here. Because it's here, we're checking first if it's next to Canadian state, okay. Then we just take this because otherwise we can have shadowing the token. We could construct it again, but okay, so for this now. This is, but so let's see. This, but let's back way. See the fields. See the other one first. This one's a mutable token iterator. Oh yeah, but I fixed both. Parse state. Ah, because parse block is a mutable self, but it's actually not anymore. So this is what I needed to do. I only know what got one error, which where it says here the state name. I mean, it says I'm borrowing here, so therefore, oh, I'm moving the value here. There we go. So therefore, I don't need to do that. Perfect. That compiles. Okay, so now we got that whole structure. We're making some progress, but now we got all the structure needed to store. Let's get back to the whiteboard so I can explain it a bit better. We got all that structure right there. Isn't it? I'm seeing the stat kinda. It's Oh, okay, yo, there's okay, yeah. I was trying to check, in the dev stream how it would work out, but yeah. Because I'm not used to it, I see like the number of viewers over time, but I was wondering if someone was in there because there's no chat, so I don't see any message in the chat. It could be that. Yeah. So that so yeah. So we got all of that. We got the parsing size. So now we can actually start parsing these blocks. That's the point. So how are we gonna do that? Because you know a block. First of all, why did I separate state from block? Because one state has only one block. That's because of branches, as we said. Because if we take, because that's actually something you yeah, get yeah gets I mean here that's how you can do compilers. Because it's through an expandable alphabet. That's what we usually do. Because if we take this code here, no, so we got state name. We got state name. We got, and then we have our functions. So we have add, whatever, sub, whatever. Then we have our f branch, which is 5, for instance. Then we got null. That way, I can refer to block specifically. Else div, and if, and what? Let's see here. We got this. So the idea is that a state, if you actually compare this properly, so we first got the state name, then all of this here is a block. And so you can define, but the idea is you can define, like if you do like proper grammar for this, you can say, you can do it like this, like state, it's a state name, and it's a block. In order, we don't care about the stops, we just have state name and block. So when we get our block, when you get our block, the block's equal to, it's probably not the exact graph, how do you write it exactly, but yeah, the blocks, it can be one of these, either it's a function call, and an argument list, or it's branch, bunch of symbols. I'm gonna also call it argument list for now, but yeah, it can be more complicated than that. And then it's branch start. That, then it's branch start, then it's and then it's a block, and then optionally we got an else, and we got a block, and then we get an end if. So so here, what's actually here? So the idea is that you start, and the program will be, and we got a program block, which is a list of states. With plus for whatever. And yeah, argument list is just it's just an argument, and then can be plus or 0. It's not the exactly how you write it, because I'm not an expert in the subject. It's been like years since I've used it like this properly. But the idea is that this is called an expandable alphabet or something like that, formal language, whatever. I know about computer science, but not necessarily all the small details of it. So but the idea is that you, when you create this, you got two types of symbols. You got terminals and non-terminals. Which one are our terminal symbols? The one I wrote in capital letters. So that's state name, function, branch, else, branch start, end if, and argument. The idea is that you continue to expand your program until it gets to that. So when I start here, I start with program. I start with program, which is a list of state. I can expand it then. You know, that's the first step. Then second step, I'm gonna use layers to explain that. So then, second step, I'm here. I got one state name, and then I got a block. So I'm expanding that block. So we keep state name. I'm gonna erase just behind that. So we got the state name block. Very good. And now we will be doing the. And now we got the and we expand our block. So we expand in a. Actually, the block is a list of statement. It's a statement, and there can be several. And statement is that. Okay. So yeah. So the idea here is that I'm not gonna say exactly how we do this because that's what we do, but I mean that's the whole compiler. That's what we do from the start. So the idea is that we take one of these statements. It's a statement. This is a statement. This here is also a statement. But we get that statement. So we got that. Okay, perfect. Let's expand it to that next step because we got statement, but now we know what type of statement it is. So it's function here. You know, I'm matching the characters. Function and argument list. I'm gonna write them here. Function. And then we get here it's a branch. Which start. And then we get our block, but here we got an else. Here we got an end if. So we match on this. We usually what you do to understand which block it's gonna be is that you look at the first token. If it's the first token, it's a function. You know we're gonna be working with the block function. If the first token is a branch, we know we're gonna be doing with this variation, which allows us to match it verbally. And so we got our arg list. We got another block. We got our arg list. No, we don't have an arg list. Sorry, I'm just writing nothing. Here's the arg list. And now we're expanding again. That syntax because we found argument, 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 maybe. But yeah, so we already did that, and then we continue to export tricks. So we got function, and there we go with our arg list and arg list. Okay, well. Okay, well, and at this point you just then once again expand that. You continue to expand until you arrive at the end where you got what you get. Well, you get a full program. This program's fully terminated. So that means, and that's how we matched everything. if at some point we can't match, we report errors, but as long as we can keep expanding the alphabet, that's what we do. And actually that's why I want, and you can see here, so you can say, okay, well, cool. Why why are we interested in that? It's because it maps really well to because once you have this alphabet here, it maps really well to this function. Because if instead of because it sounds like really complicated, but think about it in in a programming term. Imagine basically you're trying to return these final tokens or whatever you read from that, but imagine now that each one of these non-terminal symbols is uh, well a function. So that means you got your function program. You got program. We're gonna segment, and you're like, yeah, well, my program, it's I'm calling state until I can state as a program we'll call we'll first we'll handle the state name, and if it will call the block function, and the block function will continue with the statement list and all of that, and that because here's gonna be all control flow, because here when I'm gonna do this, because here I did the parse state. You've seen this function here is parse state that we just programmed. That's why I did all of these. I probably should have explained that earlier, actually, because you probably just went in and looked at me do that without understanding what I was going on. Sorry. Let's just say I'm tired for the 12th time this day, and get some compiler theory now rather than later. I think I can put a flux marker. Whatever. But yeah, this is compilers 101. I mean, more than 101, but yeah. This is the parse state function we actually made. That's why I'm trying to match. That's why the first thing I'm doing here is matching that state name token. And that's why I'm doing that here. I'm doing all of that. Do I get my state token first or not? Actually, now that I think of it, we're kind of missing a couple tokens here. Because yeah, that's the. But yeah, because we can well, I'm setting it up. But yeah, we got our parse state, so that's what we do. That's why we parse the state here, and then we parse our blocks separately. So while our language here, if we do just one simple thing, it's gonna be okay. But that's why we get but this allows us to compose these functions, which is why we get the parse block just later, because well, parse block, it's gonna be called several times here, because okay, I'm doing the because here parse block is gonna do that statement on its own. The language simple enough that we can kind of mix the steps here without having too many things. But that means that here that's parse block, and we match this. Oh, and there's a branch. Well, we match the branch, but here these two are blocks. These two are again parse block calls. This is recursivity, which means we call parse block from within parse block. You can see here like branch. We will match the branch token, and then we will do parse block again. More likely we do a parse branch function too, or something similar. Because let's be honest, the functions here they're quite simple. Like we already got everything we need from that. What we actually need that will be complicated is the branch, because that's the only control flow we have actually. That's the rest just instructions that will get translated directly. So that's why we're gonna be keeping on doing that. Okay. Well, now that uh, now that we have that idea explained properly, well, first of all, we're gonna be able to do that, to implement that parse block function by matching to a token. So if we find a function token, if we so token type function call, if we do function, it's just let's not eat that token just yet. I will do that because we let each function do. But here we match the function. Here, if we find the branch start or branch on its own, what's on it? What was the token like? I forget. Branch, and then it's branch start. Okay, yeah, branch. It's got this branch type. We match the branch. On all the other cases, we don't know what we'll do yet. Actually, we have an error. Yeah. In this case, we will do an unparsable token. So at the moment, we're only testing with the scripts that work, which, I mean, that's a kind of a cop-out in if you think about it. But also, do we really have an issue with it? Fellas, not really. But yeah, actually, here that's can pass an empty script. Okay, well, yeah. That's okay here. Well, here, however, it's not correct. So we're gonna have to create a state before we. Yeah, here we do need to add a state. I'm gonna do it in to do because let's be honest, not a big deal. Because here someone can send us a bad file, so we can't really just crash. But this is not gonna slow us down, and because this is kind of polish, the to do allows us to know that we crash here before we have any problems, and we know what's going on, and that way someone can come and be like on the Discord and be like, "Yeah, I don't understand why is the engine crashing," and we get the trace directly to that, which is kind of nice. But yeah, now we pass the block. Actually, let's even get started on tests. With an end-to-end test. I know, not yet. We're just gonna trust our instincts that we're programming correctly, which of course we're programming correctly, and here, of course, I program correctly. I never do mistakes. We don't really need all that self-reference now that I think of it, but yeah, actually, let's remove that. I don't think we need it because of course when we get errors, we will send it to them, but at the moment, not really. We got a compiler, a vector of compiler errors, and see, do we parse of function, and we get a semantic element. Actually, yeah, no, actually, that's one of these cases where we will get a result because we do these one by one, and that's why the stop token is helpful, because if we get an error, we do send back this. We want one compiler error because we do that, and we will continue. Okay, we probably still want a vector of compiler errors, or because we might get several ones if on statements that are really complex. But parse function. We don't need a parse statement because it's not like we got statements elsewhere. That's a block is just a bunch of needs. So we don't need that granularity like we did in that example. But yes, so well, here in that case we just get just one error, so we just declare it when we go through it. But this function, the parse range, this one gonna be requires us to do much more. We're not doing it today. We're doing functions now, and we do that way we can get to the compiled code as fast as possible. So if we match a function, we do semantic representation parse function. But to be honest, we don't need that to be inside of semantic representation. That could go outside of it. Well, details. It's not like it really matters. To be quite fair. It's an associated function, that's just a way to keep it, but we already are in a block that's here, so to be quite honest, I probably will want to split this into two files. That's maybe yes, maybe not. Because all these parsing ideas kinda takes a lot of room or not a lot of of reason because I'm gonna want to do the analysis too, but that's gonna make it a bit tricky to work with. But yeah, well, for now, let's keep it all together here and refactor after that. So let's first. That's where a function that just. Let's start making more functions outside because I think that's. Expect. So expect token. Expect token just gonna send us an error, a result with an error back, but so yeah, because the idea here is just simple. It's like get a function name, and then it's get the argument list. Of course, that's not the trickiest function in the RAM. So, but I'm trying to think of how I'm going to do it, in a cool way, because I want to expect a token of type function call. But that's but actually that's kind of like a match expression. It's not like I can just give it like this because it's not really like so. Let's see if it works. Let's see if it works. Let's see if it works. It probably doesn't. It definitely doesn't. Okay, whatever. On the enum constructor. Yeah. At this point, we know we have a token, right? So in this case, we will won't use an helper function. We will just do it like a regular way, which is doing. At this point, we know there's a token, so we can unwrap it. And if we don't, well, uh, that's will pass something you can cache in. basically if it's the end of a block or that we have an end of statement, we stop. That's a way to get to that. Hmm. I can still get my expect token, which is gonna send me back my token type, because if I need a token instead, I can just get it directly. Just token dot next. Cool. As a result, it's either a token type, uh, vector of either arrow. Therefore, I'm like, just let is the vector of let's get my get doing a lot of boilerplate, but that's just because we want it to be user friendly at the end. So that's why we get a lot of these atrocities. Fuck. Because you can't really match exactly to an expected token, but we can take the token type from it, which is in general what we want. You know, but in this case, we only get token. So we don't have these, but we can do. But we can do that here. So which is, in the other case, we just do air vector driver. Because this is usually something you kind of want to have in some way, but as an helper. But here in this case, with the way we have it set up, if you're rewriting code, it's a good idea to start first without knowing exactly what you're doing. That way you'll be able to restart to rewrite code every time. Okay, expected token. Now we got function name here. So in this case, we got our function name. Now we can get our argument list. Ooh, okay. That command doesn't need to be there. It's obvious enough. So while let I'm gonna put these out too because I'm bored of writing. Anyway, there's some helper function. Get them out. Next token. If the next token is the end of the while it's not the end of the statement. This. We do get our arguments because we're gonna need to pass them to the function, of course. Because we know we are gonna have one, so we can unwrap it. Now let's match. Let's match the type of the token. So if the token, so we know it's not the end of the statement, so that means it's a token that is useful. Because we do all of these first, that means that the core work becomes a lot more easier to do. Which is why we want to, while you program, you want to cut all the edge cases as soon, and you want to set yourself up for success, which means that setting up the core of what you do to be clear, because that's what we're gonna change. Like if we got a lot more complex argument list, for instance, well, that's where it will be helpful. So if we match the token type of argument, Do I just push the token type if it's just an argument? Let's not. Actually, let's just push the string and clone it. That way we'll actually be able to do something about it. There we return this 70 element. And return a function, a specific element. Let's see. But if here I'm using a lot that structure here. Let's extract it here. We don't need that error message anymore. We have access to it. Let's just send it like so. Let's see how many errors we have. 6. Okay. 62. Knowing the token type. We got the functions we got here. We don't need that, we just format it. It's already showing this 4 errors. Okay, it's 141. Initial passing stays, but This is gonna be much easier to test just in a bit. I could probably rename the Lexer to mod Lexer instead of having a file like this. Do the same to semantic. It's one of these that's while we got the test here in one module, which is nice in terms of if it's not directly, it's hard to you can't really get access to it. You know, kind of makes the whole structure a bit more annoying, especially because if everything's called mod.rs, like it's gonna be a mess in my editor. You don't really see it, but yeah, don't want everything to be called mod.rs. That's gonna be real fast. But if you got 2 entries for each one, that's also annoying. But yeah, I mean, a minor annoyance. Pass block, okay, yeah. Function. And at the end of these, we return OK semantic element function. I didn't check if it was possible. It's not a type. Yeah, okay. I was curious, and apparently you can't. So that also means here what we actually return is a result. That also means semantic element. Okay. That's not a big deal. Should be borrowing the type indeed, and I'm actually start okay here. Okay, cool. There we go. It's already here. Let's do for the whole semantic. We'll put all of this in a parsing. Yeah, all of a sudden, this is a lot nicer to see, and this means we will be doing it in a much it will be easier instead of having all of these top. while here in the parsing block we have all the, okay, let's also declare the mode parsing, otherwise it's not compiling. That's why we are undeclared type. Okay, yeah, well. Is the only we'll see if it's all needed or not, but for now let's just do that. 5 errors. That's already what to do. Use of undeclared. I'm parsing. This gets me at and whether this is semantic. This is Alexa. Also use that. Private function, yeah, of course it is. Cool. That means we'll be able to implement this. So now it's 4 p.m. here. Which is, I mean, am I still feeling alright? I'm still feeling alright. Let's see here. But to be fair, right now, like we don't have that much information on it. I'm kind of wondering if it works as expected, which is likely to be. So we don't even need that. We just need a parse state. This is the public interpret on this. But yeah, well, let's assume it works. No problem. We'll find out soon enough if it doesn't work, but at this point, that means we got our vector of semantic elements, which is not complete yet, because a function, because all of that work was to handle errors properly with all of this, which is why it wasn't writing vector of string. Random parsable is just a string. Okay, perfect. A branch gonna have a pointer to how do you call that? Into a block. It's gonna be horrible. Oh, it doesn't need a pointer. I guess you can get it immediately. But there's the if else branch and there's the multiple branch. That's kinda how it goes here. The branch, first of all, there's the later, but you go. Condition true and false. While this one is gonna have it bunch multiple condition and the vector of we don't have a lot of information on that yet. As usual, let's get to it when we get to it. So yeah, okay, so at this point we have our vector of semantic elements. The, right, well, actually, in the parsing here, at my function, okay, I'm getting in the function call, so now I have my function, and I got my arguments. It can be an empty vector, that's okay, that's what we want. And then we're gonna validate that everything's working properly, which means we need to check if every functions exist and if there's no issue. We still need to send back some information actually, because we got some errors. We're sending back our single compiler error, but we want to append it to the ones we get. So we pass the function, we get an error. Okay. So parse function, we didn't stop here. We did match our semantic element. Now it's about bringing it back home until we get that semantic block out of there, and then we give it to the state. So we do the parse function by sending the tokens. At this point, what we have here as a type is a result. So because we are assuming that's here. So if we have we could do a match of matches, but let's not. Let's do here. Let's do it like this. So does the semantic block have errors? No, the semantic block doesn't have errors. Why did I put that as a separate element again? Yes, there. Oh yeah, compile. I want to be able to compile the elements of a semantic block separately. Okay, let's go add element. And if it's an error, if we're returning a single one, oh, your branch can serve on several errors. Cool. Done. We're done here, and now we match until the stop token. The bug before it happened. Okay, so now we're matching up to here, and we get until that stop. So yeah, that stop token is coming in clutch. But yeah. like that. We also send back our errors. So that's good. Now we got that. And we got our blocks. That's exactly what we needed. So that means that now parse state works as expected for a simple use case. Now, and now we're gonna add the errors. So upon add state, what's this? We're gonna have the errors as yeah. Well, let's add the errors again. That way, it's easier. Okay, so even though they will be in double, let's do self.state. No, self.errors append. Yeah, state.errors clone map. No, I don't think it's clone. That's just because I'm gonna clone it here. Uh, here it's I think that's the one I said. Yeah, this message. Yeah. So we gotta do an iterator first. I can figure it out. Uh, and after that, I collect. Okay, cool. So now, that's the 66. Okay, so cannot go as breathable. Okay. Yeah, there we go. We got we got our block parsing done, and it does bring back all the errors as expected of it. And when we add state, we get the errors too. Okay. So now we got our initial parsing function done. Therefore, now it's time for the semantic parsing. Does the function make sense? Probably. Do we need it like that? Okay, so whiteboard. I'm starting to get a bit hungry, so might not be a long while before we stop for today. It's also been, well, it's been 4.5 hours for someone that's still a bit, I'm still having problems from yesterday, so that's a very nice day of work. Especially you're supposed to take breaks and not do a straight up like 7.5 hours like I did the other day. That's not what we meant by a full day of work. Remember, that's not days of work. Don't work like that. Anyway, so remember our steps for semantic representation. I prefer the green pen. Semantic representation. What? For semantic representation, we got several steps. So first of all, we got that initial parsing. So what the initial parsing did is that we got all of that into some semantic states, blocks, elements. Basically, we already got our state representation. So that's what we want. But then we want the second step, which is take that semantic representation and enrich it. Want to enrich those elements to see, well, if it works, enrich it and check. For correctness. That means we check our method here, like the add method. Whereas the not method, because if we here we say, oh yeah, that's the add method. How many arguments does it get? It gets the correct number of arguments, and we are very satisfied with it. While if no operation is here, that means we don't actually, we say, oh wait, that's even if it's correct, like this function doesn't exist, let's not do that. This would block the last step, which is state realization to Castagne compiled code. Fifth one, which is just Cask to Cask. Yeah. So from there, what do we do? Where do we go? Simple. It's gonna be simple, fellas. We're gonna do I was thinking a bit too further ahead about execution. Don't worry about that. But yeah, we're basically just gonna check if the functions exist. This is because yeah, that's kind of the only thing we have left to do, if we're quite honest. Because we have every semantic element to check. Because we can't do it. The reason we can't do it here because there's variables, and at this point we know what the variables are. We can find a symbol table of these, which do help a fair bit. Yeah. So because without that symbol table of function and the list of functions and all of that, we can't check the list of functions we are supposed to have. Although if we are using like if we're doing something more advanced like calling states like we would call functions, which will be something where I will add to Castagne. That's gonna be quite exciting. That won't be. We also need to learn them before. So therefore we do check it at this point, and we check with every. You're gonna check every one of them. So it's gonna be. I'm trying to think of exactly the structure, because remember, a function call. Function call, right? Yeah. At this point, we still have only strings. Strings and we call that and the argument list, and which is more strings. And the thing is that I'm gonna want to check that string, see if it's in the function list, and then well, if it's validated, actually, what I probably want to do is something is to get that ref to the casp function, in question. If not, and for the argument, an argument's a string, but I want if it's a little depends on the argument type too. Like I kind of don't want to do that every time. I want to have my argument list and be like, yeah, that's my this argument, this get actually. That's why I get my casp func. I got a reference to the casp function, and I got a list of I got a vector of cask vars. Because once I got my cask variables, that's where the fun begins. So yeah, at this point, I need to make my variable, my symbol table, all of that. It needs to be done here, and once I have here, actually, I'm gonna do these two steps at the same time, because that's what I do. I do that because and that third step's actually just gonna be export, because I want to store this information. Like, yeah, that's me. Because once I get my cask function, and my cask vars, because I do get them, I have enough information. I'm passing it right there and now, and I'm adding that directly to the state. Yeah, that's how we'll be doing this. That means the state needs to add the semantic state now has another thing, and it's a cask instruction, which is going to be vector. It's going to have its commands, of course. Yeah. Let me try put another one of those marqueurs de flux, as it says in my page. So, because the cask var, as you can see, there's the own with the usage, because we already have that index, and we can go back and forth through the symbol table. And well, what function does what? That's we can find the link at a later point. Because otherwise, that would mean because yeah, we don't need every semantic block to have its own script and stuff, because that's what we'll do the commands here like that. Okay, cool. Do we want, that means do we want the semantic elements to be able to parse themselves? Or we export that because we don't have access to that symbol table? Yeah, let's do that. Let's do gonna get a better name for that, but also we're gonna get it. We have our symbol table. What? Where is it? State table. Okay, whatever. We don't have. Let's let's circle back to that later and just brute force that whole thing. Uh, for let's just ignore the variables. We'll compile the state, which is again it's gonna be like it's probably actually something we also want to have in a second file. Once again, let's because every state is gonna compile by itself. Because once again, that's something we can do. Although although there is gonna be like some interdependency between them, which is going to be an issue potentially, which is uh, which is something we will handle at the time it needs to be handled. So every state will be able to be that way once we have that dependency graph. But at the moment, we have no dependencies. Therefore, it's not something we need to concern ourselves with. I do wonder though, if if this way of doing is not gonna come and bite me back later. Because if I'm compiling everything and removing all of my metadata, do I really get the, can I really do that? Like, of course, I'm gonna have that and symbols and stuff, and but like I think knowing the branches is gonna be quite useful. But whatever, if we can extract the code at this point or at the later point, but yeah, that means I probably need to bring the comments not per what do you call that, per state, but per block, which is not gonna be an issue. Right, block, uh, which is of course potentially returning issues. So actually, let's not compile that block. Let's not change anything. Let's just, no, actually we want to change it because we want, if there's a subblock, we want to be able to change every one of the beats. Yeah, that sounds very complicated, but we'll manage. We'll manage. Let's be honest, by the way, we probably don't want to validate here, so let's assume all of these is already done, like, because if the initial parsing had errors, if the initial parsing had errors, we would just panic at the moment. Let's just do it properly. That's fine. At this point, we know that at this moment we kind of on the happy path. Just glad to get this. Don't care about if it's compiled. That's what we do. And here we're gonna because at this point we know that every one of these exists. So we just assume we can create our simple table and dependency graphs. If we can't, that means we don't yet know exactly. Maybe that's yeah, that's a second step. Register symbols. And therefore we suppose we already have all of that. Suppose we probably could have an error because that's basically what it is. I'm gonna program in C right now. Can I just make one of these? Done. Okay. Previous cell, missing comments. Okay, yeah. Fair enough. But we actually don't want it in the semantic state. Okay, yeah, I can do this. But I'm not handling that error, which isn't good. What was the what was in that? It's not a part of the whole book. That's the whole book. Because I did read that there's some way, somewhere in this book, there's a way that you can tell it to compiler instruction. I don't know who they called actually. That's macro. So the book of host macros. No, wait, not actually. I'm looking for all the macros. Okay, cool. Oh, advanced feature, yeah. Oh, that might be where I found it. From attributes. Okay, that's an attribute. want the list. I don't want the. Didn't it have one here in the STD? STD modules. Because I think there was a macro module. Maybe it's in the prelude though. Trading. Oh, yeah, there we go. It's not that, because we have the derived macros and all of that, it's attributes. Good, thank you. So, built-in attributes, yeah! Yes! We got that. Put it in the bookmarks. I mean, there's one viewer, so if the viewer can see what I'm trying to get. Oh, that's it's gonna be like a Dora the Explorer. Like, yeah. Actually, oh yeah, it already works because it's already a result. Okay, perfect. That was already. That's nice to know it's already there. I don't need to think about it. It's not like the error. I mean, we just know there was an error, and the errors are stored here. Which I don't know if it's very rusty, but yeah. We're just gonna expect everything. The previous cells. Okay, but of course because we don't. This one can stay. Yeah. Register symbols. At the moment, we don't have any symbol table. We just hard code it. It's gonna be okay. And compile this one's. Let's return error for now. But because we're not okay with this. Do we do now? And here. Okay. There we go. We compile. So of course we compile it. For compiling, of course we will get get this. We're gonna compile the states, of course, which is gonna, I mean, we're gonna add other things, but we the state with semantic state. It's gonna go with the result. Which is wrong also here, right? Yeah, of course, returning compile block state dot block. Here we're returning okay for now. That's what it compiles. Actually, we do because we're clean. And then from here we're gonna add. Can I just do it like this? Compilation should work in theory. One previous error. Expect unexpected answer. Okay, yeah. Then no. I can do it like this. I can use like this, but I can declare my modules like this. Okay. Well, we did all of that effort to get those errors back, but at the moment, let's just crash when we get one. That's gonna be easier. I'm bored of it. I've got enough errors for today. Let's call it like that. State that iterator, but mutable iterator. For state in self, and there we're compiling compile state. Oh, but I guess it is already a mutable iterator. Can I get that? Does that work? First of all, it won't work because it's not a public function. WSL compilation, yeah, okay. What do you mean string? Why do I have a... Huh? Oh. Oh, right. Yeah, because it's a hash map. There we go. Okay. Let's do it in order. I think I can return just one compiler. No, I can return several because several arguments can be wrong at the same time. It's not. So, compile block. So for each one of these, let's get our command. Yeah, we don't want to keep it. It's with each function. Come on. I don't want to hold everything in one function. Because an enemy here, we got all of the semantic elements. But a lot of them are gonna be like, we're not all gonna have that thing. Yeah, each block is separate. We can optimize them separately, and when we get a branch, we will see. So this is where we put our command. And therefore we will do we do the semantic elements for element in block elements. I'm guessing this is what we want out of the no, that's a semantic module. We got our element, but a semantic block is a vector of elements. Yeah, this is where we get our commands though, which is going to be a vector of yes command. Oh, although is because I'm gonna have yeah, that's actually very bad here because when I have those elements, what I want to is a bit of an improved block, you know, not just the semantic elements, but I want to have the associated command. But yeah, I do want it separately. Uh, I do want it a bit separately because if I get all these, like the problem is that if I keep the because it's a block and not a state, that means that it covers the you can have a branch right in the middle, and we don't want that. Therefore, pardon. Therefore, we actually want each semantic element to. It's actually want to tuple the semantic element the and the associated vector of cast command that goes with it, which at the beginning is nothing. In fact, we could probably, instead of having a tuple, we could probably do a bit of a better thing. Uh, Probably want maybe a structure here. It's a compiled block, I guess. Because I kind of want, you know, to be able to go. I mean, I need to be able to refer to it whenever it needs to. I can probably make them as blocks and other blocks, you know, separately. You know, cut it where there's an element of the correct idea. But because yeah, I do want every semantic element to be associated with cast commands, which I can't really do from the enum. I mean, from the enum, it just gets that. Actually, it does. That's probably a semantic element still, instead of semantic compile block or semantic compiled element, which is maybe a whole lot other thing. Not the semantic type. You never know how much data you need with these things. So the element type is a semantic element type. And here we also just get the semantic element type. And we don't even need that, let's just keep it simple. So yeah, we get in somewhere already. Of course, this has changed the thing massively. Let's do. It doesn't blow up in our face when we fire, because here let's get the errors early, because now that we have semantic element types, and we add the is 65, 48, 22, pas de 48, 22, 40. Probably the field file. Hop là. 5, 15. Ah, I forgot. I think that's this one's a bit different. It's argument incorrect here. The method takes a semantic element type, so that's why it doesn't work. And which one? What? And single error. Perfect. Now that we have it here, so let's continue. It's as you can see, there's a lot of stop and go. That's I mean, that's not an issue. That's just with falls at times. That's why we will be working each one of these. God, don't need that too much yet. Wait, this also allows us now to have our elements get uh, additional ideas here, because in the semantic tree here, I'm gonna have element because we don't want people to get access to that, to the type. Yeah, type's okay, but comments is not, because comments can be branch, and if we get the compiled code from the branch, that's gonna be a whole lot of things. But here, in this case, we can. That's not an issue. Not fun. We iterate mutably on that block. So this one, each one of these elements. Just match on the type of the element. And with that, it's gonna be like I don't know what I'm supposed to do here. That should actually we should be able to match all elements here, so that should be unreachable. In actuality, it's just I mean no actually because we will know we don't need a default case. I'm just trying to get in. We match on that result, and if it's okay, then the element commands of the element is gonna be it's gonna be the commands we got here. That's why all these functions would give us back this. But if it's an error, yes, it's simple enough code. If we don't match, we just don't match. Here it's error dot append. Assume that. Why does it work? Mentionable expression, okay. 16. Correct. What's the last one? Okay, that's I really like the to do macro. It's really smart also with all the how it's implemented with that exclamation point type, like wildcard or whatever. Now, if we get semantic element type function call, don't care about what we match inside of it. I guess we can leave code. We do let equal to function. That singular or macros let's see. Actually that's very useful for this. It's not that it's we're not having an error, we're just panicking. That way we just get it done. Yeah. Of course, here we're if you remember, I said we were going to get this, so we're gonna do this. It's gonna you're just gonna match it and say it's we'll just say it's good enough. We always use the first one, and we'll make tests that will fail as soon as we want. That way, it's gonna be much easier. Hi, Crimson Guitarist. Thank you. At the end of the day, but we managed to. What is to do here? just assume. You just hardcode the number of arguments too. Because of course, the Castagne function can have a lot of declarations and types and all of that. But at this moment, we just get one number of arguments, and then we'll expand on all that. Until we can compile, maybe not the exact same behavior, but we can compile similar behavior to what we did in the past. Like, I want most of the functions to work as expected. Which is why we got here. We could use and could try parsing the said arguments and seeing if it matches the function definition. Where do we put that? That's another thing. Oh, we can put it here. It's here. So this here is you're gonna of course check. You're gonna then this one's gonna be interesting. So we don't want to compile an argument. Taking an argument and we make it into a cask variable. Of course, here it's going to be a result of either cask var or a compiler error. We don't need a million compiler errors here, just once, and then good enough. So So okay, we add all cast var to the argument list, and if it's an error, we return vector containing that error. These, those, and this allows us to, at this point we have all of the arguments. Then we'll match on definition and we'll see just if, because at this point we already returned, so we know something's gonna work here. So if arguments from length is equal to gas function dot nb. The problem here with the cast var is that it's a bit don't have the type yet, but everything in its time when we get to that variables and all the variables with their values. Because if you remember, like the cask var is not a variable we already have. It's the memory entries. We want the memory entry type. Like we want to match on that, not the current value, just the type. If it's an integer, if it's decimal angle, if it takes a numeric or whatever. If it takes any numeric, that also works. But we get to doing funny things with information things later. At the moment, we're just still bringing back the basic functionality online. At this point, we know that our function is valid. So we do want to convert it to Castagne script. And therefore, this is the moment of truth, the moment where you actually get this, and we send it on up. So yeah, we got this. It's a cast parse function. So therefore, can I just call that closure like this? Maybe. Ten errors. A bit more than expected. Compiler name 27. Oh, because it's a let list, I forgot about that. Creation line 30. And 21. Thing on is there. Okay. There's a couple of things. First of all, here it's a format. Forget also the format here. Here's okay. I'm gonna have to make the singular a generic. I think that's how it works. Did it work? Weird. Nice. It's a field, not a method. Okay, that's how you call it. Fair enough. Oh, and this is the one missing. Argument to cast var. That's exactly there. Okay. Oh, okay, well. Maybe I can just clone this out. Okay, well, that's so it can't do that, but that's because we didn't derive the clone yet. Ooh, good. So from then on, the cast bar here is not. We're getting it. We're gonna use that argument here. We're gonna kind of brute force that whole thing. But because ideally, maybe if we know what we expect, we can kind of do a bit better. But at this point in time, because this can be because a cask bar can be a lot of things, and maybe that's not the right interface for that, because if we get because some of these we want to be fairly constant, that might be a weird memory entry type, you know. Well, well, now that I think of it, we also have constant cask bars, so therefore that's kind of not the most important point. Okay, so I was thinking of some optimization for later. Let's just just pass it, like we're not even sending back a compiler error. We just wait. No, actually, we don't want to do that. We want to go and match with the argument and send in whatever value. So if we got A, we're sending a cask var like own 0. And here we're sending it to the loop. One, two, three. And with that, I think we got that. It's time for the test. Oh wait, no, we still gotta get our unoptimized code. That's how we will get through this. And we are sending back a state table. Oh, it's this test not gonna be conclusive. Yeah, that's why it's gonna be like let's not even make this. Let's just keep it here. At this point, we don't have a lot going on. We don't have enough going on, especially because it's gonna be changed immediately. Why is it gonna be changed immediately? Because we're gonna change that immediately because we don't have anything yet. So we can do we don't have all of that. We're kind of just hacking it together to see if we can get the compiled code. And once we get the compiled code, we want to see if it runs. That's the trick. We just want to see if it runs and if it does the one thing we called it for. So therefore we're gonna do like so here's our code. Start with the state name and we do add A, B, C. This should give us the semantic thing. Passcode, then we execute, and then we check result. Check result. So to passcode, let's bring back the semantic representation as semantic representation. So that and so to do that, we take this one. We take our semantic representation and pass next script. Here. This gives us some semantic representation. From there, the semantic representation gives us an optimized code. Okay. Then we do the execute, which we know we can do because we have we did it in the next test. This is one I want to see. Yeah. No. Engine test. Test engine cast script. Yeah, I'm gonna send it to cast script here. What's with the engine with cast script? This one's quite useful actually. Probably gonna do a better testing. the memory stack. Let's just get that guy. Let's get that guy here. Get rid of okay, so the state table, that's hmm. Okay, so there we go. We have the engine, and that we can use that to test the engine. Hmm. This shouldn't compile because we forgot to import everything. And then in the compilation we forgot to put an OK around everything else. Okay. And that means it's only me. State doesn't have anything. Forgot. I got like redfish memory, clownfish memory, whatever. Can't even remember that. Yeah, of course we don't because we don't have the state script. So it's for each state. Using that a lot. Let's do that so it's a bit more fancy. not really handling any errors on top of that. Okay, so I'm assuming there's no else here, but we'll get to that. We're cloning the commands because why not? It's not like we're gonna have to. And there's not really heavy, and because we're gonna be copying them quite a lot. So commands dot append mutable reference to element. This will give us some code. It will work. It will work always. Therefore, therefore, uh, yeah, that's kind of almost it. What's the last ones? Last few things. Look. Okay. There's lots of small errors. Let's see what it tells me on the second screen because it's a lot of small stuff. Let's just get through it fast because I'm starting to get tired. I mean, I already was tired, so I guess I can continue for hours. But let's finish. I mean, early. It's been 6 hours, no breaks, no eating. Yeah, that's definitely the end of the day. Let's just finish that. And take a nice evening. I forgot just the self here. Uh, because I don't forget that. Yeah, we just get. Oh, several elements that iter, yeah. Expected boolean. Okay, yeah. I got a lot of errors that have come just from the has errors function. It should return a boolean. Let's put it earlier in the. Sort of. So it's because the cast command should be cloned and compiler should be clonable. So compiler error, that's here, debug clone. Of course we do want that. Then additionally, I guess we can also do partial equal and equal. That's a good combo. But then we also got, of course, our cast commands, which are not here, which are in the here, which should actually implement the derive. So they got partial equality, they got equality, and they got clone. Let's say that. Do they get copy? Let's not have copy. And it's not really. Well, this is working, but the command itself, because there can be the closure. That's why we don't want it. The closure, there can be 12 warnings, 23 errors now. 23 errors. Let's it's the same one. It's the same one a bajillion times. Because Casva can clone, but it can be partially equal and equal. Now, only one error, which is 184. Stay.get unoptimized code. Should be good. Oh, right. Cool. Now let's see cargo test. It's not compiling because, of course, not compiling. We are not using anything. I mean, it exists, but it's not accessible. Let's state table definitely. Then previous errors. Use RC and RFCell. Okay, so now we have our full test, and we ended up. So let's see line 58 of parsing. This was peculiar. Does that work? Found stop Stop. It's probably, most definitely, yeah, there's a stop after. Oh, this one. It's in the, because we get a stop just after this, and yet we still immediately do that. With the server. Yes, okay. Okay, so that's not what happened in that case. That means it's not this. We'll trace execution using printf. Function call. Okay. And then for the stop. That's not good, and that's actually a why does it get a stop actually? That's oh yeah, and then here I want to get the next token, because now that I've got the next, now that I know that the next token is the end of the statement, which is actually a good question. Why doesn't it? Oh yeah, it's in case there's an error. In case there's an error, we continue until we find the stop token, and then we eat that stop token. Wait, but we might not know. Anyway, that's actually no, that's a mistake. No, recovery. What's the issue today? Expect a token. Yep. Yeah, they've got expect token or something. Expect token function, yeah. Sweet tokens one. I should have had a token iterator actually. Let's see, expect token, use it only once. Okay. If I want, yeah, that's better be a option. That doesn't really help much, but anyway, expect token. That's a bit more fluid. Yeah, I can't really do much here because the token type can be a lot of different token types. We can do that. It's just a small one. The previous cells. Wells. Let's see which. Okay, superb. So semantics 996. So we're getting an error at the initial parsing stage. You can have errors, but that means if any one of these steps returns an error, we still get the semantic representation and we get the errors in a way that's easy to check. Therefore, now in our file, which file it was again, 8 errors, but that's a lot. Okay. First of all, let's put it in the. We got to put it okay. Oh yeah, because in my that should be still good. Errors, let's see. Previous cells. Okay, I see the mistake here. I gotta put another pairs. Which one are they? And they all take only one. It's a tuple. The previous cells. Errors in the code. Okay, very well. Know that we can actually display all the errors we have got up to now. And of course, we have to implement the display for compiler error, otherwise can't print it. I think this is the same for the function signature. For okay, one error. Use std from display. Okay. Parameters. It's got a result. Okay, that's not that. Okay, let's check. Let's check an example, because we love example. Let's ignore that for now. We can still get the debug and have it error free. It's already got debug here. Oh, I'm getting trolled by my own code. No, no, come on. I put that thing. Anyway, it's not like there's not special statement. Let's go. Okay, what's the errors in the code? Yeah. What? I mean errors in the... Oh yeah, not the other errors in the code. Errors in the code. Then on that's even errors in the code. Okay. Okay. But I have no idea what the errors in the codes are. That means that I think there's just no errors in the code, but it's staying. We've got the sending back an error. Who is trolling me with this? To do get an optimal key, yeah. Wait, what? Um, I got it in 4 places. As else here. It's to be fixed. If it has errors, it's here. If it has errors, I'll send it here. That's okay. Not yet implemented. No, that's a new one. You're sending in the state table. Let's go. Let's go. I expected there to be a bug, I expected there to be a bug on the execution, but no, we got it. That's the test. Yeah. Yeah, that means that we actually got the compiler implemented. Not fully, of course, but the compiler can now produce Castagne script code. That means we got that thing down. Let's do a final whiteboard session and then leave for today. But yeah, final whiteboard for what we'll do the next time. So, okay, so today what we did was the lecture was already done. So lecture already done, but we did go over it. So we got that semantic representation. More specifically, we got this first step, which was to check the grammar. Then we didn't really check too much. We did like temporary checks logic, and we got and of course all that with error reporting, which is a big part of it. And then we compiled said code, which is very nice. So that means that now what you can do in Castagne, like right now, Castagne has both a working VM and a compiler for said VM. It's both are incomplete. Both are incomplete, of course, but that means you can already execute code, and we have code that came in and that did check, they did execute one frame and it did work. That's honestly that's really nice, especially for 2 days of work, 2 days and a half, maybe let's say three for the if I was working like regular employed hours, that would be 3 hours, 3 days at least. But yeah, we got. So that's very 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 nice. So what do we want to do now? So there's a few options for what we'll do the next time. But what next is, well, there's branches. We want to implement them faster, earlier than the later. But that's not the top priority right now. There's a much higher priority, which is going to be to have the variables. Variables should exist in this. But yeah. Variables should exist in our Castagne code. And that because at the moment we can hard code everything, but this means basically we produce a better state table, but somewhat, but mostly like this symbol table that we keep talking about. So the symbol table, in general, the symbol table is the variables, but it's also, now we said it's not the state. The state table also goes here because it's gonna be all states, but we can keep metadata and stuff. But yeah, basically this is what is the next objective. That's declaring the variables. In Castagne, we also had this. This was done through the use of variables block. If a block starts with variables, that's where you find them. It's either called variables just by itself or variables with this. So this is what we're going to add to that. This is what we're going to add. Maybe like that means that maybe parse state those check the type of the state before parsing a block, because that might not be a block. That might be variables, because if you have, because for a regular state that's a block, and here we have variable, which can also happen in a block, but we'll get to that later, and that's not a quick fast thing. We get variables first. We just declare everything at the start. Kind of like that's very close to the early days of Castagne, because there was nothing. There was just nothing. So you just did what you could with what you had. But that's still going on very well. The next step, of course, is gonna be, because once we have the variables, we also know the types of the variables, which, I mean, the branches, we can implement that, but let's first focus on the functions. So we want functions that are better, that are more advanced, like functions and validation. Why do we want that? Because the add function, for instance, the add function can take two arguments, either an int and an int, or it can take an int, and an int. And I want, of course, that function declaration to be quite more powerful, because if we don't, that's kind of that's not that useful. The thing is that we might want to change our let's see, we might want to change our parse function to that, because we want to get maybe, because we want to get the check function that will return either a result, either it's okay, and it returns a parse function, the parse function we're gonna use, or it's an error and it will return the error. More likely, I mean, the result. So that means potentially adding a new closure, but whatever. But we will bring an additional function on this interface, and we will get some new ways of declaring, because that's going to be part of our user interface. It's a declare with one list, which is going to be archetypes and defaults. And then we can of course then do to declare several options, because that way we can match whichever one works better. We test several, and we take the first one that does work, maybe something like that, or we declare with a custom. So that's one way, and with that will be quite far already. And then there's the modules, because until we have modules, we cannot not doing anything, because as soon as we got modules, we can put basic functions, which is pretty nice. We will start with state transition. Well, we will start with states in general, because otherwise, what are you going to do? But we'll start with states, and then the interesting thing is that we will also be able to have physics from the module. But the module, so it provides the functions. That's nice, but it also provides some variables. And we'll have to decide on that interface, because the variables will also go to there, because it's like if we declare them first. And once we have that, there's already a lot going on, but we also shouldn't forget to have multi-file support, which is gonna require additional work in the character, and that's gonna be the biggest one of the biggest hurdles, because that means we can start to get we'll start to get overwriting and all of that. For the moment, I think the order for everything like this should be number one. We can do either of them, but I think number one should be the variables here. That's the number one thing, because once we have the variables, we have the symbol table and the state table, which is needed by this one, which is gonna be our number two. It's gonna be these functions. Then it's gonna be either of these two, because this one impacts a lot the design. This one impacts a lot the design too. But since both impact the design a lot, I think branches, let's get the full language stepping up inside of one thing, and then we'll do the multi-file editing. Finally, we'll be going to modules. Hopefully that makes some. Once we got that, of course, we got the optimized code already. We got plenty of cool stuff. Because we got that, we of course need also at some point being Uh, being when we get some more now we got. I'm trying to think when we will get like better tests because as you can see the test I did was very rough. But yeah, we'll iterate with time, but with how we go. But yeah, variables. That's gonna be a whole thing because we're gonna have to go back to the lexer, and then we're gonna go back to the semantics, and then we'll also need to go back to the tests because now we get the symbol table and the state table that goes with it, and so we will be able to interact with more. And with that means we'll also go back to the memory setup, memory from a symbol table. But yeah, you guys, I mean, a symbol table. Now that I think of it, a symbol table is kind of just like a memory, but it's kind of like a memory, but it has no types yet. It has the default variables. That's just, I mean, you can create a memory from a symbol table. Yeah, that's exactly how we are gonna do it. The state table is not super important right now, but yeah, that's gonna be another big one. I mean, pretty much everything's gonna be a big one here until we. And it's only once we get everything up and running that we will get some smaller tasks, like, I don't know, moving a character around. But to get to moving the character around, there's also still many steps. Okay, let's get a quick view of what are the steps in general. So we got, and then I'll be going. So the main steps here, like right now we're doing the engine core. Engine core. That means here we want to build to run a real Castagne character. Doesn't mean it's not gonna do a lot of stuff, but like I mean it's got states, it's got a skeleton, and uh I don't know. I mean yeah, that's about it. It's got states and a skeleton. That's already nice enough. And yeah, it's from CASP file. So currently we're definitely in that. But the next steps. So that's where when the modules are done, basically that's the steps after the module here is just I guess it's just the core module, maybe physics. That's gonna be like I'm gonna keep with the green. Maybe physics, but I'm not sure if I'll put physics yet. Then there's several ways to continue this, but the most logical of them all would be to do the Godot bindings. So we run Castagne from Godot. Another option, of course, that means this one also means that we got the graphics module. That's a bit of an annoying part, but yeah, whatever, we'll manage, and we'll also have bindings in the Rust version. But yeah. So next up, after that, there's the editor. the editor's gonna be, there's one very tricky part, that's connecting. Because at this moment, I want Castagne to be a bit more independent on the engine, for better, to be able to run a bit better by itself and be in general a bit more chill. But the editor is always gonna be in Godot, regardless of if you're using Castagne in Unreal or whatever. I believe it's better if the editor is always in Godot because we don't want to do that several times. So ideally, that means you can able to connect to a process or relaunch it. It also helps that it's not inside of the we are not inside the project itself, because that way you can do more around the project. What I mean by that is that, well, uh, right now, if you want to restart, if you want to change the model, you're obligated to restart the whole Castagne editor. If I do that and I manage to control it to puppet it from the editor, that will mean we can iterate a bit faster and we can unlock some additional ways to work. But yeah, once we got all of this is where development really gets going. This this all here, that's phase one basically, and that's the minimum. I'm set up. That's also because we also, by the way, these two here are gonna be very annoying because you know what? Because we're gonna have to make it work on Linux, Windows, and I mean macOS. I'm not doing that one myself, but I'll try to have, if someone, for instance, Snuffy or others are using macOS, they can go figure out for themselves where to. Uh, Thank you, Daniels. Dallas Daniels, which one I should say, but yeah, just saw the message. I don't see the messages while I'm doing the thing here. Yeah, so this is the minimum setup. Once we get that, we are able to continue, and because of course then there's the actual stuff, everything, because we got the input module, we got, well, actual graphics in general, we got the editor tools, uh, plenty of that. Of course, the editor is gonna be, and once we connect the editor, that's most of the work done. But I mean that's the trickiest part. Got that flow control and back and forth. We can even get at first. You're not even gonna be able to edit code from the editor, so it's gonna be a bit of a misnomer. But yeah, doing the editor tools, doing the editor UX in general, and all of that good stuff until we get some good feature parity with what we currently have. There's also AI, stuff like that. And once we have that, then we can do documentation, tutorials, and general improvement. Yeah, and that's I'll probably publish a first version at some point, somewhere around here, probably for one first Godot 4 version. Uh, Once we have all of that together, that's when we can actually start distribution, which is gonna be one of the most annoying parts. Distribution might be a bit off stream because it might require a bit more of just elbow grease and being on my stuff that's more specific to my computer and not the project. But we'll get to that when we get to that. All of these here, that's the. But this is the definitely more interesting part. Next stream is whenever I work next and I'm in a good enough disposition to stream. So yeah. So thank you everyone for tuning in. I hope you enjoyed that stream again. And well, let's hope the next one will also be quite productive.